All right, so my research was concerned with the 2D angular rotation of the Bohr models for non-equilibrium orbitals. So, as many of us are already familiar with, a Bohr model is basically just a two-dimensional representation of how electrons at different energy levels orbit around the nucleus of an atom. However, we run into some problems with this model because it doesn't accurately describe the path the electron takes, nor does it describe the radial motion as well. So to address this problem, we use quantum numbers, which I have listed here. A lot of us are already familiar with, but the scope of this research is to model how in particular how angular momentum affects how the model or the atom rotates at different energy levels by the principal quantum number. So we define angular momentum as a vector quantity, which is the cross product of the radius from the center of the atom and the momentum. And because we want to define this in a x and y position space, we use the z component and take that as our angular nodes. And in order for the atomic orbital to be stable in this space, we need these node values to be whole numbers. Otherwise, the atom will just essentially collapse on itself. With that in mind, we can then use a wave function, a trial wave function, and convert it into polar coordinates in terms of the azimuthal angle and the distance from the center, as shown here, taking into account both x and y components. So for the method, we use MATLAB to simulate cycles of this rotation for node values are 1.1, 1.5, 2.1, 2.5, and so on. And the parameters we use for this are the total kinetic energy, which is defined by the x and y components of this kinetic energy. We use initial wave functions defined in terms of position in the x and y space, and we use that to convert these vector quantities into essentially a super operator, where the unity matrix is essentially a matrix that has ones along the diagonal and zeros everywhere else. With that in mind, we can then define potential energy as central, attractive, and coulombic as a four-dimensional supermatrix defined by indices I, J, I prime, J prime, and that is equal to, and basically it's defined along the diagonal, where if the indices are not equal to each other, then the value is 0, and which means that our Hamiltonian superoperator will be equal to the kinetic energy if the indices are not equal to each other. We can then use this Hamiltonian to give our time-dependent Schrodinger equation with the evolution operator to model how it propagates along space over time. And then we can also use this Hamiltonian as a general solution to our time-independent Schrodinger equation to model our two-dimensional eigenstates and eigenenergies. So now we can model yeah. Did you get the updated slides I sent you? So I thought I sent those, but if I can play most of these at once. So as each video progresses, we can see that the nodes that are closer to a whole integer remain more stable, and the nodes that are fractional kind of dissociate over time, and towards the end just completely becomes a mess. There we go. So now that we have that in mind, we can also plot the eigenstates of our electron of the simulated hydrogen atom over time by plotting the diagonal of the potential energy of the equation as shown in the previous slides when I went over the methods. So this is what that graph looks like, and we can see that as time progresses, it kind of makes like a step up going through time. And when we plot the two-dimensional probability density of each state, we can see that it corresponds to, or it resembles certain orbitals of atoms at different energy levels. And then we can then compare that to those orbitals of a hydrogen atom and see that they are very similar as their orientation in space and of their energy levels. So to kind of summarize it all, we use MATLAB to essentially simulate how angular momentum affects the angular rotation of an atom, and we found that the atom destabilizes if the node values are fractional, whereas whole numbers are more stable and they retain their shape. We also simulated how two-dimensional, or how by plotting two-dimensional, or plotting the eigenenergies of this atom in a two-dimensional space, it should resemble that of the orbital shapes at each given state.
Okay, please join me in thanking Joe for interesting presentation. So, are there questions online? Are there questions in class? Oh, okay.
You can go back to the slide where you had the orbitals overlaid on the eigenstates. So you have them listed as like dx, dy, fx, fy. Those are just the orbitals that are in the xy plane.
Yes.
So they, okay.
Microphone. Or just approaching.
Yes, so the px, py, dx, dy, that's just their orientation on the xy plane.
Okay, so a little comment to a question by David. Most merit and satisfaction of curiosity from work by Joe, it is how hydrogen atom in two-dimensional world would look like. So there is no out-of-plane motion. Therefore, there are no z component.
Yeah, I was just, it was entirely me just looking at it and trying to relate it to the three-dimensional models that most people.
And it is a very beautiful discovery. Like if one changes number of dimensions, then the Aufbau sequence that we all were taught from kindergarten, like 1 S2, 2 S2, 2 P2, is violated. And here is something new because of different dimensionality.
So is there a reason there's only one 4D?
I believe it's
maybe he didn't explore further states. There are like 1,000 states, and he displayed only first dozen.
Yeah, that's about it.
Okay. More questions? In the audience, I do have one. So by looking on this beautiful image, I make just a visitor to the class. An interesting observation: as we go from lower states to higher states, they occupy a larger and larger area, more and more distant away from the center of atom. So how would you interpret or explain this observation?
I would likely explain it as the electron gains more energy, it has more freedom to overcome any forces that are bonding it to the center. So it is able to break essentially that energy barrier that has been kind of mentioned in the past.
Okay, yeah, excellent. So you're telling kinetic energy overcomes potential, and balance of centripetal and centrifugal moves this away. Excellent. It's really great. More questions to Joe? If no, please join me thanking him once again.